in the vast theater of the universe. Our solar system is but an inconspicuous stage in the corner. For a long time, we thought planets, orbiting stars, was the ordinary script of the universe, until we pulled back the curtain and saw much more bizarre performances in the distance. And among these jaw-dropping discoveries, one planet stands out. It challenges humanity's established theories of planetary formation with its unique pink hue and bizarre origins. It is the exoplanet GJ 504b, a rebel star that belongs to no existing script. To truly understand the uniqueness of GJ 504b, we must first look at its home. This planet orbits a star named GJ 504. Located in the constellation Virgo, this star is about 57 light-years away from us. This distance is practically right next door on a cosmic scale. But under humanity's current technological conditions, it remains an insurmountable chasm. The star GJ 504 itself is slightly hotter and more massive than our Sunday, a stable star in its prime. Through precise observations, astronomers found that this star is very young, roughly between 100 million and 200 million years old. This age for a star is equivalent to the human infant stage, and for the planetary system surrounding it, this means everything is still in the chaotic and active early stages of formation. It is exactly in such a young system that the discovery of GJ 504b appears so earth-shattering. The discovery of GJ 504b is itself a technological triumph. It was captured via direct imaging by the Subaru telescope, operated by the National Astronomical Observatory of Japan. It is necessary to explain here that mainstream methods for discovering exoplanets, such as the transit method or the radial velocity method, all indirectly infer the presence of a planet by observing changes in the star's own parameters. This is like guessing if there is another person next to someone by observing the swaying of their shadow. Direct imaging, however, is different. It attempts to take a direct photograph of the planet itself, separating that person directly from the background. This technology is incredibly difficult because planets themselves do not emit light and only reflect the extremely faint light of their stars. Furthermore, their proximity to bright stars in the sky makes it like trying to observe a flying firefly right next to a searchlight. GJ 504b was, at the time, one of the lowest mass planets orbiting a Sunday-like star discovered through direct imaging. This achievement marked a new level in exoplanet detection technology. When we first saw GJ 504b, the most surprising thing was its mesmerizing pink color, like blooming magical cherry blossoms. This color is not an artist's imagination, but the result of scientific observation. A planet's color is closely related to the composition and physical state of its atmosphere. GJ 504b appears pink, mainly because its atmospheric clouds are thin or have gaps, allowing us to peer into its deeper, hotter inner atmosphere. These deep atmospheres are rich in gases, like methane, under high temperatures, and lacking reflective cloud layers, such as the ammonia ice clouds we are familiar with on Jupiter. They absorb blue light more strongly than red light, so the reflected light takes on a warm pink hue. It is like a giant, newly formed, and yet too cool ball of gas, showing us its blazing interior. What truly puzzled and excited astronomers about GJ 504b is not merely its color, but the baffling distance between it and its host star. The orbital radius of this planet is very large, about 43.5 times the distance between the Earth and the Sunday, on the scale of our solar system. This position extends far beyond the orbit of Neptune, almost entering the realm of the Kuiper belt. According to our most classic and successful theory of planetary formation, the core accretion model, the formation of a planet begins in the protoplanetary disk surrounding a star. In this disk, dust and ice grains collide and stick together, gradually forming larger and larger planetesimals, ultimately coagulating into the cores of rocky planets in the regions closer to the star. If these cores are large enough, they can rapidly accrete massive amounts of gas from the surrounding disk, forming gas giants like Jupiter. This process usually occurs in relatively dense regions closer to the star, typically within 10 to 20 astronomical units. But in that distant realm where GJ 504b resides, the material density of the protoplanetary disk is extremely low, and the frequency and time scale of material collisions are far from sufficient to form such a massive planetary core. It's as if we found a magnificent modern metropolis deep in a sparsely populated desert. According to existing theories of urban development, this is almost impossible. Another astonishing characteristic of GJ 504b is its mass. Initial observations estimated its mass to be about 4 times that of Jupiter, but subsequent, more precise analysis lean toward a lower value, roughly between 1 and 2 Jupiter masses. Even so, it remains a bona fide giant planet. The combination of immense mass and a distant orbit creates a sharp contradiction, directly pointing to the Achilles' heel of our planetary formation theories. If the core accretion model struggles to explain its birth, then where exactly did it come from? This brings up another highly debated theory, the disk instability model. This theory suggests that under certain conditions, especially when a protoplanetary disk is massive and cool, it will rapidly collapse under its own gravity, directly fragmenting into one or more clumps of gas, which subsequently cool and condense to directly form gas giant planets. This process is extremely rapid, like a blitzkrieg in the cosmos, capable of creating giant planets in the vast regions far from the star in a very short time, on the order of thousands of years. GJ 504b is very likely a cosmic marvel born through this fast track. The existence of GJ 504b forces us to re-examine the diversity and complexity of planetary systems. It reveals to us that there might not be just one pathway for planetary formation mechanisms in the universe. Our solar system might just be one relatively neat and orderly pattern among many possibilities. In the broader universe, the disk instability mechanism may play a much more important role than we imagined, especially in those young, massive stellar systems. GJ 504b is like a messenger from the ancient past. The system it resides in is only 1 to 200 million years old, providing us with a unique laboratory to study the early evolutionary state of giant planets. By studying its atmospheric composition, temperature, and orbital characteristics, we can catch a glimpse of what a giant planet looks like in its infancy, thereby deducing the thrilling nature of its initial formation. The in-depth study of GJ 504b also relies on a detailed analysis of its atmosphere. Spectral observations show that its atmosphere may contain water vapor and carbon monoxide, but the abundance of methane is lower than the standard model's prediction. This methane deficiency phenomenon has also been found in some other exoplanets. This may suggest that there is a strong vertical mixing process in its atmosphere, bringing deep methane free gas to the upper layer, or the carbon-oxygen ratio in its formation environment is different from that of our solar system, each possibility is related to its original environment, providing key chemical clues to solve the mystery of its origin. Reviewing the short history of human exploration of exoplanets, from the first indirectly detected hot Jupiter, which has overturned our cognition, to today's planets like GJ 504b discovered through direct imaging. Every step is full of surprises and challenges. GJ 504b is not just a distant celestial body, but also a symbol of the continuous expansion of human cognition. It tells us that the imagination of the universe is richer than our wildest theories. It quietly floats 57 light years away, emitting a soft and mysterious pink glow, as if whispering to us, "What you know is just the prelude to the universe's story." Looking to the future, with the James Webb Space Telescope and the use of new generation observation equipment, we will be able to conduct more in-depth and more detailed research. We will be able to accurately measure the detailed chemical composition of its atmosphere, detect whether it has cloud structures, and even search for possible satellite systems. Every new data point may become the key to unlocking its formation, mystery, and further reshape our understanding of the planetary family. On the long road of exploring the universe, planets like GJ 504b are not obstacles on our theoretical path, but a lighthouse guiding us towards a deeper and more comprehensive truth. Its existence reminds us to keep humility and curiosity under the vast starry sky, which are always the most moving qualities of scientific exploration. Now introducing an exoplanet named Celt-9b. Its extreme environment and unique properties have become the focus of astronomers' attention. This planet seems to be a world that comes out of science fiction. Its real existing state challenges our traditional understanding of planetary systems. Exoplanets mean planets that orbit stars other than the Sun. Celt-9b is one of them. It was discovered in 2017 by astronomers through the Celt Survey project. This project uses two small automated telescopes to continuously monitor the brightness changes of millions of stars. It uses the transit method to find exoplanets. The principle of the transit method is that when a planet passes in front of its parent star, it will slightly block some starlight, causing the observed brightness of the star to have a periodic and slight decrease. The discovery of Celt-9b was made by detecting this periodic change in brightness. The star that Celt-9b orbits is a very special star. It is located in Cygnus, about 670 light years away. Its mass is much larger than that of the Sun, and it has a very high surface temperature. It belongs to a rare type of a star. These stars are hotter, brighter, and younger. Their lifespan is relatively short. Understanding the characteristics of Celt-9 is crucial to understanding the extreme environment of Celt-9b. Because a planet's environment largely depends on the nature of its host star, the most striking feature of Celt-9b is its extreme high temperature. The dayside temperature of this planet, the side facing the star, can reach an astonishing 4,300 degrees Celsius or more. This temperature is even higher than the surface temperature of many stars. For example, it is much hotter than the red dwarfs we are familiar with. As a comparison, the Sunday's surface temperature is about 5,500 degrees Celsius. And Venus, the hottest planet in our solar system, has a surface temperature of only about 460 degrees Celsius. The temperature of Celt -9b is high enough to vaporize most metallic elements, including high, melting, point metals like iron and titanium. Such extreme high temperatures are caused by a combination of factors. The primary factor is Celt -9b's extremely close distance to its host star. The orbital radius of this planet is very small, only about 0.035 astronomical units. An astronomical unit is the average distance from the Earth to the Sunday. This means the distance between Celt -9b and its host star is much closer than the distance from Mercury to the Sunday, only about 1/10 of the latter. Such a close distance causes the planet to be intensely heated by the star's strong radiation. Another important factor is Celt -9b's tidally locked state. Just as the Moon always faces the Earth with the same side, Celt -9b also always faces its host star with the same side. This results in an extreme temperature difference between the two sides of the planet. In addition to the high temperature, Celt -9b's physical characteristics are also very special. It belongs to a class of exoplanets known as ultra-hot Jupiters. This means that, like Jupiter, it is a gas giant planet, but its temperature is far higher than that of typical hot Jupiters. Celt -9b's mass is about 2.8 times that of Jupiter, but its radius is about 1.9 times that of Jupiter. This means its density is relatively low, and it is in an inflated state. This inflation is caused by the extreme heating of the planet's interior. The high temperature causes the atmospheric material to expand, making the planet's volume larger and its density lower. Celt -9b's orbital period is very short. It takes only about 1.5 Earth days to complete one orbit around its host star. This means that on this planet, a year is less than 36 hours long. Such a short orbital period is the inevitable result of its extreme proximity to its host star. According to Kepler's laws, a planet's orbital period is directly related to its orbital radius. The smaller the orbit, the shorter the period. Such ultra-short period planets are not uncommon in exoplanet research, but Celt -9b's extreme environment makes it stand out even among similar celestial bodies. From the perspective of atmospheric composition, Celt -9b provides a unique research laboratory. Through spectral analysis, astronomers found that in the ultra-hot atmosphere of this planet, substances that normally exist in molecular form are broken down into atomic states. For example, in planetary atmospheres with lower temperatures, hydrogen usually exists in the form of hydrogen molecules. But on the day side of Celt -9b, the high temperature is sufficient to dissociate hydrogen molecules into hydrogen atoms. Similarly, common molecules like water and carbon monoxide are also thermally dissociated. Even more interestingly, astronomers have detected atoms of iron and titanium in Celt -9b's atmosphere, possibly even including their ionized forms. This is the first time gaseous iron has been explicitly detected in an exoplanet's atmosphere. These metallic elements would condense into solids or liquids at lower temperatures. But under the extreme high temperatures of Celt -9b, they exist in a gaseous state in the atmosphere. This discovery not only confirms theoretical predictions, but also provides valuable data for us to understand the chemical composition and physical processes of planetary atmospheres. The atmospheric circulation pattern of Celt -9b is also of great research value. Because the planet is tidally locked, the temperature difference between its day side and night side is extreme, possibly exceeding 1000 degrees Celsius. This massive temperature difference drives fierce winds blowing from the day side to the night side. Theoretical models predict that the atmospheric wind speed on Celt -9b could reach several kilometers per second, far stronger than any wind on Earth. These winds transport thermal energy and matter from the day side to the night side. In the colder regions of the night side, some metallic elements might condense into tiny droplets, forming metallic rain, such as iron rain or titanium rain, which then falls into the deep atmosphere of the planet. The extreme environment of Celt -9b also brings about an interesting phenomenon: atmospheric escape. Due to the high temperature and intense stellar radiation, materials in the planet's atmosphere, especially light elements like hydrogen and helium, can gain enough thermal kinetic energy to break free from the planet's gravitational pull and escape into interstellar space. Observational data indicate that Celt -9b is indeed experiencing significant atmospheric mass loss, forming a glowing, comet-like tail of material. If this process continues for billions of years, it could significantly alter the planet's mass and composition. From the perspective of stellar evolution, Celt -9b's future fate is not optimistic. Its host star, Celt -9, is currently in the main sequence stage, but over time, it will evolve into a red giant. During the red giant phase, the star's volume will expand dramatically and may engulf its inner planets. Given Celt -9b's extremely close proximity to its host star, it is very likely to be swallowed by the expanding star in the future. Even if it is not swallowed, the powerful radiation and stellar winds released during the star's evolution will further erode the planet's atmosphere, potentially leaving behind only a bare planetary core. The study of Celt -9b is of great significance for our understanding of the formation and evolution of planetary systems. Traditional planetary formation theories suggest that gas giants usually form in regions far from the star, where there is enough ice and gas to aggregate into a massive planetary core. However, the presence of an ultra-hot Jupiter-like Celt -9b so close to its host star sparks discussions about how they reached their current positions. Possible mechanisms include planetary migration, while the protoplanetary disk still existed, or being scattered into an inner orbit through gravitational interactions with other celestial bodies. Observational studies of Celt -9b have also driven the development of detection technologies. Because the proportion of starlight dimmed by this planet during transit is relatively large, and its orbital period is short, it has become an ideal target for detailed atmospheric characterization. Astronomers have conducted multiple observations using the Hubble Space Telescope and large ground-based telescopes, obtaining high-quality spectral data. In the future, with the commissioning of next-generation observation equipment, like the James Webb Space Telescope, our research on extreme exoplanets like Celt -9b will enter an entirely new stage. The discovery and research results of Celt -9b also remind us that the diversity of planets in the universe far exceeds our previous imagination. In our own solar system, planets can be divided into rocky planets and gas giants with a relatively limited temperature range. From a broader perspective, studying extreme environment planets like Celt -9b also helps us understand the boundary conditions for the existence of life. Celt -9b's extreme high temperature and intense radiation clearly make it unsuitable for any known form of life. However, studying such extreme environments can help us determine the limits of planetary habitability, understand the evolution of planetary atmospheres and geological processes under different conditions, and thereby better assess the life hosting potential of other exoplanets. With the continuous advancement of observational technology, astronomers are discovering more extreme exoplanets. Similar to KELT -9b, these discoveries not only enrich our sample of exoplanets, but also provide natural laboratories for testing theories of planetary formation and evolution. Looking back at the exploration history of KELT -9b, from its initial discovery, through a tiny dimming of starlight, to the subsequent revelation of its extreme characteristics, through various observational methods, it reflects the comprehensive nature and technological progress of modern astronomy. It is not only a subject of study for astronomers, but also provides us ordinary people with a window to peek into the cosmic wonders and diversity. Now, we are going to focus on a very special exoplanet, Washington SP-39b. It is not located within our familiar solar system, but orbits a star about 700 light years away from us. The discovery and subsequent research of this planet have completely overturned our traditional understanding of planetary systems, providing key clues to uncover a corner of the universe's diversity. It acts like a peculiar mirror. Although it does not reflect the world we are familiar with, it allows us to glimpse the infinite possibilities of planetary formation and evolution. To understand the uniqueness of WASP-39b, we first need to know how it was discovered. Astronomers didn't just look through a telescope and see it directly, as many people might imagine. In the vast sea of stars, directly observing an extremely distant planet that doesn't emit its own light is a difficulty comparable to finding a needle in a haystack. Scientists employed a clever technique called the transit method. You can imagine that when WASP-39b passes in front of its host star, it is like a tiny shadow sweeping across a giant light bulb. This shadow very faintly blocks the light emitted by the host star, causing a periodic minute drop in the star's brightness that we can observe. By capturing these regular fluctuations in light, much like listening to the heartbeat of the cosmos, astronomers not only deduced the existence of WASP-39b, but were also able to precisely calculate its orbital period and even estimate its size. However, the true charm of WASP-39b goes far beyond how it was discovered. Its physical properties are a cosmic spectacle. It is a typical hot Jupiter, meaning its volume is similar to that of Jupiter in our solar system, but its orbit is extremely close to its host star. Just how close? It takes only a little over 4 days to complete one orbit. In contrast, Mercury, the closest planet to the Sun in our solar system, takes 88 days to complete an orbit. This extreme proximity brings about a blisteringly hot environment because it is tidally locked by its host star's gravity. Washington's SP-39b likely always faces its star with the same side. This subjects its day side to continuous, scorching stellar baking, reaching unimaginably high temperatures. While the night side is relatively cooler, it remains a high-temperature world. This environment is completely different from any planet in our solar system. Another astonishing feature of WASP-39b is its puffiness. Although its mass is only about 1/4 that of Jupiter, its volume is even larger than Jupiter's. This means its density is extremely low, making it a highly inflated gas planet. You can think of it as a giant balloon floating in space, puffed up by high-temperature steam. This fluffy structure is closely related to its internal high temperatures and the intense radiation from its star. Scientists believe that such close-range roasting causes the planet's atmosphere to heat up and expand, forming the massive volume we observe. This provides an excellent natural laboratory for studying the physical state of planetary atmospheres. Under extreme conditions, if the orbit and physical characteristics of WASP-39b left us amazed, its atmospheric composition truly excited astronomers, arguably opening a new era of research. In past observations, our understanding of exoplanetary atmospheres was very limited, like looking at flowers through the fog. But technological advancements, specifically the deployment of the James Webb Space Telescope, have completely changed this situation. The Webb telescope, with its unprecedented sensitivity and infrared observation capabilities, acts like a precise cosmic scalpel, able to dissect the mixed light from WASP-39b and its host star to analyze the chemical information hidden within. When WASP-39b passes in front of its star, the starlight passes through the planet's atmosphere before reaching us. The various gas molecules in the atmosphere act like specific color filters, absorbing light of specific wavelengths and leaving unique fingerprints, absorption lines, on the starlight spectrum. By decoding these complex fingerprints, scientists can deduce exactly what chemical components exist in the atmosphere. It was through this method that the Webb telescope conducted an unprecedented, detailed, cosmic physical examination on WASP-39b, and the results of the report were astounding. One of the most striking discoveries in this report was the clear presence of carbon dioxide. This was the first time carbon dioxide had been clearly detected in the atmosphere of an exoplanet. This discovery is of great significance because it indicates that complex chemical processes, which we previously did not fully understand, may also be occurring in the atmospheres of gas giants. The discovery of carbon dioxide not only proves our ability to detect key life indicator molecules in distant worlds, but also provides new clues for understanding the formation and evolution of such planets. But this was just the beginning. The observational data from the Webb telescope acted like a treasure map, guiding scientists to discover even more atmospheric components. In addition to the expected water vapor, researchers surprisingly detected the presence of sulfur dioxide. This was the first clear detection in an exoplanet's atmosphere of a product generated by photochemical reactions, driven by the host star's high-energy photons. Simply put, the intense ultraviolet light emitted by WASP-39b's host star acts like a catalyst, breaking down the structures of molecules like water vapor in the atmosphere and releasing active components like oxygen atoms. These components then react with other substances, such as carbon monoxide and methane from the planet's interior or the primordial nebula, ultimately synthesizing sulfur dioxide molecules. This process is called photochemistry. Its discovery proves that in the dynamic environments of exoplanets, there exists an active and complex network of chemical reactions, far exceeding our previous simple assumptions based on planets within the solar system. Furthermore, Washington's Sp-39b's atmosphere also contains metallic elements like sodium and potassium, as well as carbon monoxide. It contains other metals like sodium and potassium and carbon monoxide, especially in a ratio relative to hydrogen and oxygen that is much higher than that of Jupiter in our solar system. This seemingly minor detail hides a massive secret about the planet's origins. It serves as a piece of cosmic archaeological evidence, telling us that WASP-39b may not have been born in its current orbital position. Based on these chemical clues, scientists have painted a picture of WASP-39b's likely life history. It was probably born in a much colder region, far away from its host star, where it was able to accrete a large number of icy and rocky planetesimals, rich in heavy elements like carbon and oxygen. This process is similar to how the giant planets in our solar system formed beyond the snow line. Subsequently, due to some dynamical interaction, such as a gravitational tug of war with other giant planets, or drag from the gas in the protoplanetary disk, it began to migrate inward, eventually being flung into its current scorching orbit, right next to the star. It swallowed a massive amount of solid material during its formation, which explains why the proportion of heavy elements in its atmosphere is so high. This planetary migration story, though still partly hypothetical, is currently the theoretical model that best perfectly explains its observed characteristics. The profound significance of studying WASP-39b goes far beyond understanding the planet itself. Serving as a benchmark, it has greatly propelled the development of the entire field of exoplanetary science. First, it validated our technological capability to detect and analyze the chemical composition of exoplanet atmospheres, going from only being able to measure size and mass to being able to detail an inventory of its atmospheric components is a qualitative leap. The Webb telescope's success with WASP-39b marks the official entry of exoplanet research into a new era of atmospheric characterization. Second, the in-depth study of the photochemical processes in WASP-39b's atmosphere provides a crucial, intuitive reference for us to understand other types of exoplanets, especially potentially habitable rocky planets. Photochemistry produces aerosols and tiny particulates, which affect the temperature structure and energy transport of a planet's atmosphere. If we were to discover potential biosignatures, like oxygen or methane, in the atmosphere of an Earth-like planet in the future, we must first be able to distinguish whether these molecules originate from biological activity or are merely the result of inanimate photochemical reactions. WASP-39b is like a selfless mentor, vividly showing us how these complex chemical reactions occur in a non-biological environment. Looking to the future, the story of WASP-39b is far from over. It will continue to be an important target for astronomical observation. Deeper observations will help us accurately measure the abundances of various elements in its atmosphere, and perhaps even map out a three-dimensional structure of its atmosphere, from day to night, from high altitudes to deep layers, to understand how heat circulates on this scorching world. These data will continuously test and refine our planetary formation and evolution models. More importantly, the successful study of WASP-39b points the way for our next steps. It proves that we possess the technology to detect complex molecules, which fills us with confidence in ultimately finding signs of life on a more Earth-like, temperate planet. When we face a planet that might harbor life in the future, everything we have learned from WASP-39b, how to decode spectral fingerprints, how to understand photochemical processes, and how to deduce planetary history through atmospheric composition, will all become the cornerstone of our judgments. Finally, what we are going to visit together is not a scene from a science fiction novel, but a very real, incredibly bad, tempered world. The exoplanet, HD 80606b, with its extremely radical and crazy behavior. It completely subverts our traditional understanding of planets, showing us the diversity and incredibility of cosmic celestial bodies. In the early 21st century, astronomers captured the traces of this planet using telescopes at the Lick Observatory in California, USA, through precise radial velocity measurements. It orbits a Sunday-like star named HD 80606, located in the constellation Ursa Major, about 190 light-years away from us. This star has a companion star, HD 80607, and together, they form a binary star system. This might be exactly the root cause of HD 80606b's bizarre fate. Imagine that in our night sky, near the handle of the Big Dipper, hides such a cosmic marvel. The most striking feature of HD 80606b is its jaw-dropping, bizarre orbit. Most planets in our solar system have nearly circular orbits, which keeps the climate relatively stable throughout the year. But HD 80606b is completely different. It travels along an extremely elongated elliptical orbit, with an eccentricity as high as 0.93. What does this mean? It is more than 10 times that of Mercury, the planet with the most elliptical orbit in our solar system. The shape of its orbit is more like that of a comet than a typical planet during its 111 Earth-day orbital period. It spends the vast majority of its time lingering in the cold, deep space far away from its star. Then, in an incredibly short period of time, it hurtles toward its sun like a cannonball, completing a thrilling perihelion sprint. The direct consequence of this orbit is the most violent and insane seasonal change playing out on a cosmic scale. We can imagine it as a superclimate disaster lasting for several weeks. When HD 80606b is at the aphelion of its orbit, it is far from its host star, receives very little radiation, and its surface temperature is around 500 degrees Celsius. While this temperature is still scorching, it is not particularly outstanding among the exoplanet family. However, when it begins its dive toward the star, the situation undergoes an earth-shattering change. On the day it gets closest to the star, during the few short hours it passes perihelion, its distance to the star shrinks drastically to a mere 0.03 astronomical units. How close is this? It is over 20 times closer than Mercury is to the Sunday, and only 1/30th of the distance between the Earth and the Sunday. At such a close distance, this planet meets its moment of judgment. The side facing the star is directly subjected to the roasting of stellar radiation, and its temperature skyrockets at an explosive rate. In just a few hours, the temperature can instantly jump from a few hundred degrees Celsius to an astonishing 1,200 degrees Celsius or more, possibly even reaching 1,500 degrees Celsius. This speed and magnitude of heating are unparalleled in the known universe. Such drastic temperature changes trigger global, super powerful storms on the planet. Imagine half of a planet instantly being thrown into a steel furnace, while the other half remains at a relatively low temperature. The massive temperature difference creates an unimaginable pressure difference, which in turn drives a destructive reorganization of the atmosphere. According to computer simulations by astrophysicists, supersonic hurricanes will form on HD 80606b, with wind speeds potentially reaching several kilometers per second, many times the speed of sound. These storms are not only incredibly fast, but their scale covers the entire globe. frantically sweeping the blazing hot gases from the day side to the freezing night side. The entire planet's atmosphere is as if placed inside a cosmic scale blender, undergoing an endless, violent cycle. This extreme roasting mode is not continuous because it is tidally locked by the mother star's gravity. Just as the moon always faces the Earth with one side, HD 80606b likely also faces its sun with a fixed side. This results in its extreme yin and yang sides, near perihelion. Its day side is in a state of continuous ultra-high temperature, while the night side is relatively cool. But the violent global storms somewhat neutralize this temperature difference, forcing heat to be redistributed across the planet's surface. However, this neutralization process itself is a meteorological event full of violence. So, what force shaped HD 80606b's rebellious orbit? The answer likely points to its binary star system environment. Its host star, HD 80606, and the companion star, HD 80607, orbit each other. This stable stellar dance, however, can cause gravitational perturbations to a planetary system orbiting one of the stars. An astrophysical process known as the Kozai mechanism might be the culprit behind the scenes. Under the long-term, subtle interference of the binary system's gravity, HD 80606b's orbit has been gradually and continuously stretched and squeezed. Ultimately, from what might have been a relatively normal circular orbit, it evolved into the extremely elongated elliptical orbit we see today. It is like a ball being tossed back and forth beside two dancers, involuntarily forced onto this crazy orbital path. To unveil the mystery of this planet, astronomers have utilized the most powerful observational tools. Besides the radial velocity method that initially discovered it, transit observations have provided crucial information. When HD 80606b passes in front of its host star, it faintly blocks a portion of the starlight, causing a periodic, minute drop in the star's brightness. By precisely measuring these transit events, scientists can not only confirm its existence, but also calculate its actual size. Observational data shows that HD 80606b is a typical gas giant planet. Its mass is about 4 times that of Jupiter, and its volume is slightly larger than Jupiter's. It belongs to the hot Jupiter family, but it is a member with exceptionally outrageous behavior. Deeper observations came from the Great Hubble Space Telescope and the Spitzer Space Telescope. Spitzer's infrared eyes were able to directly perceive the planet's thermal radiation. It successfully captured the astonishing process of HD 80606b's infrared brightness, exploding several times over within just 6 hours as it approached perihelion. This was the first time humanity had so clearly seen an exoplanet undergo such drastic climate changes on a real-time scale, providing the most direct observational evidence for theoretical models. This data is like a videotape recording the planet's weather changes, allowing us a glimpse into its furious heart. As we cast our eyes to the future, more powerful telescopes will bring us a clearer understanding of HD 80606b and the entire field of exoplanets. The James Webb Space Telescope, with its unparalleled infrared sensitivity, will be able to resolve the atmospheric composition of this planet, and indeed, the whole exoplanet realm, in unprecedented detail. Aiming for a clearer understanding, it might be able to detect how various molecules in the atmosphere are torn apart and recombined under extreme high temperatures. It may detect metal oxides like titanium oxide, and vanadium oxide, and even map the global distribution of surface temperatures and storms on this planet. Every such extreme planet is a natural laboratory for testing our theories of planetary formation and evolution. Looking back at the discovery and research history of HD 80600 and 6b, it is not just a record breaker, but also an awakener of cosmic thought. It tells us that the forms and fates of planets can be so diverse, far exceeding the imaginations we base on our solar system experience. It challenges the inherent boundaries of our concept of a planet, prompting us to ponder just how many bizarre events we have yet to discover in the vast universe. Its very existence declares that the creativity and diversity of the universe will always be richer than our boldest guesses. For those of us living on a temperate blue planet, the story of HD 80606b is a soul-stirring cosmic journey. It makes us realize that our solar system, this stellar system with orderly orbits and a relatively mild climate, might not be a universal phenomenon in the cosmos, but rather rare, tranquil harbor. The next time you look up at the starry sky towards the Big Dipper, perhaps you can imagine that 190 light years away, there is an ill-tempered planet performing its endless, furious dance of scorching heat and freezing cold, and exploring such worlds is precisely the meaning behind our continuous gaze into deep space, not only to find answers, but to discover more, and even more wonderful, mysteries